Infinity can fascinate anyone who tries to imagine the number 1000, then a million, then a billion. So you keep trying step by step to really imagine the quantity. After a few steps, you realize that no matter how many you take, infinitely more remain. This thought experiment of always being able to add another number is certainly convincing, but there is a so-called infinity paradox that makes us doubt the existence of infinity. Imagine a person and a turtle want to have a race, but because the turtle is naturally very slow, it gets a bit of a head start. Now, after the start signal, the person eventually reaches the position where the turtle was at the beginning. Of course, the turtle has also advanced a little. Next, the person will reach the turtle's new spot, but by then, the turtle will have moved ahead again. That should actually go on forever, for an infinite amount of time. So, as it looks here, the person could actually never overtake the turtle. You can try it out yourselves. The next example, the universe. Is it infinitely large? In 1823, Heinrich Wilhelm Olbers showed with a simple example that the universe cannot be infinite. If the universe were infinitely large, then it wouldn't be dark at night. There would be an infinite number of stars, and the light from each star would have enough time to reach Earth, which means that in every direction we would only see the light of the stars, and the sky would never be dark. But the Big Bang Theory says the universe must be infinite. Everything began with the Big Bang. It brought space, time, and matter into existence. That means the universe is already everything. We simply live inside it, and this is all of existence. At least, that's what people think. However, one also wonders where exactly the universe is expanding into. Is it possible that, for some reason, we simply can't imagine that there is an upper limit, for example, when it comes to numbers? It's against logic, but at this point, it's appropriate and interesting to ask yourself whether there might not actually be an infinite number of numbers. In mathematics, infinity is used constantly in calculations. Many things are considered there for both finite and infinite sets. Dimensions are considered. Negative infinity, also hard to imagine, is used in calculations too. What exactly is negative infinity? Couldn't we somehow transfer that to our real life? Towards the end of the 1880s, Georg Cantor discovered something even more shocking, namely that there are multiple infinities. That was a groundbreaking realization, because we can't imagine that either. People wondered how there could be more than one infinity. Cantor developed set theory, creating objects representing infinity, such as the natural numbers. With infinite sets, you have the problem that a proper subset can be just as large as the set itself. Consider this interesting example. If you look at the natural numbers starting from 1 and the integers, at first glance you might think there are twice as many integers as natural numbers, and another which is 0. But that's just one way of writing the natural numbers. You could also write them like this. That way, you would have matched every integer with a natural number, meaning the sets are equal. There would never be a number missing from the natural numbers, nor from the integers. After all, there are infinitely many of both. It follows that there are exactly as many natural numbers as there are integers, because two sets are equal if I can map their elements 1 to 1, that is, match them up. And that's the case here, even if it's hard to believe, because you can see that the natural numbers are definitely included in the integers. The same goes for the even numbers. You can clearly see that the even numbers are included in the natural numbers. There are as many even numbers as natural numbers. Because just like before, you can match every natural number with an even number. The same goes for prime numbers. Cantor also showed there are as many rational numbers as natural numbers. So the fractions are included as well. That's even more unimaginable. Cantor had to make a list of rational numbers so that he could assign a natural number to each rational number, just like in the previous example. He first created a table like this, where the denominator increases to the right and the numerator increases downward, both going to infinity. If you were looking for the number 41,332, for example, you would have to go 332 steps to the right and 41 steps down, and you would have the number. If you had infinite time, you would make the list as follows. You go in a zigzag pattern and write down the list. You start with 0, then 1. After you write down a number, you also include its negative. The 1, 5. And the -1, 5. Then the 2. And the -2. Next the 3 and the -3. If a number has already appeared, like in this case the 2 or the 1, you don't write it down again. That's how you would continue, and the list would be complete. You would have caught every rational number. So you can again match every rational number with a natural number, which means that there are just as many rational numbers as there are natural numbers. That was Cantor's first diagonal argument. In the second Cantorian diagonal argument, Cantor proved that there are infinitely more real numbers than natural numbers. In that case, a higher infinity occurs. He demonstrated it by first taking only the range from 0 to 1, including 0 and excluding 1. He showed that even within that interval, there are already more real numbers than natural numbers. That means compared to all real numbers, there must be even more, infinitely more in fact. So he assumes that such a list exists, like before. You write down a real number for each natural number. Suppose for some reason these real numbers are matched with the first natural numbers. Then you look for a number that is guaranteed not to be on the list by looking at the diagonal. Here's how you do it. 0 point, and you look at the first number. There's a 9 there now, so you write down any other number, for example 0, and you keep going like that. Next, there's a 4, so write a different number, like 0. Of course, it can happen that at some point there's a 0 there. Then you simply write, for example, 1. If you keep going like this, you'll definitely have a number that's not on this list. This list could never be complete, so there can't be a list of real numbers from 0 inclusive to 1 exclusive. So even in that interval, a one-to-one correspondence isn't possible, because there would always be a number that's not on this list. The infinite sets Eben talks about are called countable, because if you had enough time, you could count them. But you couldn't count the real numbers, not even from 0 to 1. That's why the real numbers are also called uncountable. With that, he proved that there are multiple infinities, or rather, that there is an even higher infinity.